Okay, so we're ready to go.
Yep.
All right, awesome. So, hi guys, I'm Felix, and today I'm just going to be presenting a workshop on functional equations. So this is going to be I guess a key topic when it comes to stuff like the Simon Myers math competition, just a general math competitions. Right, that's weird. Okay, yeah. So let's start with what is a functional equation? Well, a functional equation is basically an equation where the unknowns are functions rather than a traditional variable. So I guess like starting from like what year 4, you learn about like basic algebra, a plus 1 equals to 2, that means a must equal to 1. And that's an equation where we're looking for a traditional variable such as a, right? But functional equations, they're a little bit more special. They're special in the fact that we actually have to look for a whole equation, right? And these are a couple examples of what a functional equation looks like. We have basically an f, right? And f represents a function that we don't know, but it's defined by a key set of like rules, right? So as you can see, f of x, y is equal to f of x times f of y, and just a bunch of these, right? Can anyone guess a possible solution to these functional equations? Just like type it in the chat if you have any like clue. Anyone? Okay, that's all good. Well, maybe we'll have a look at I guess this last one, right? F of x plus y is equal to f of x plus f of y over 1 minus f of x times f of y. That actually reminds me a little bit about tan, right? When we take the tan of two numbers, we get this function where f would be just tan, right? So yeah, this would be a possible solution to this functional equation would be tan of x, right? And when we have a look at functional equations, we're not usually just given this one piece of information. It's like when you're integrating something and when you're integrating an indefinite integral and you get a plus c, sometimes we have a few more rules, like a few more bounds that help us determine what specific function it is. So in this case, we have the first thing that that is important, which is the domain and codomain. As you sort of remember from, I guess, math 1a or math 1b. And the second thing that's also important for a functional equation is the value of f at some number. So as I said, with an integral example, this provides us, I guess, a more specific version of the function. And the last part is obviously the main functional equation. So those are the few sort of rules that basically just define the function. Oops. Okay. Actually, just back to this, right? A more special functional equation is this fourth one here. This fourth one is actually known as Cauchy's functional equation. And if you remember from, I guess, math 1b, this actually is like a linear transformation, right? Because f of x plus y is equal to f of x plus f of y. And this is very similar to, well, actually, like a solution to this would just be y equals cx, right? It's just like the basis of all like linear functions. Okay. And so, yeah, I've talked about Cauchy's functional equation. And what we're going to do here today is we're going to try to prove this. And for the, I guess, whole real number field. And to do this, we're going to start off with just a smaller set of numbers. We're going to start off with, I guess, a few values, and then we're going to move up to the positive integers. And from there, we're going to extend it to the negative integers. And then we're just going to keep going to rational numbers and eventually get to the whole real number field. Okay, so yeah, so a general tip with functional equations is we can always sub in numbers to get, just try to find out more about a function, right? Like, I guess when you're first learning how to plot y equals to x squared back in like year 8 or year 9, we start off trying to plot it by just, subbing in random numbers like x equals 1, x equals 2, and trying to find the y value for that point. This is really similar. And it just really helps us, I guess, solve the functional equation. Can anyone suggest what number I should sub in first to find more about this function? Wait, can I access chat? Well, yeah. So, oh, yikes. Okay, now I can see chat. Okay, yeah, 0 is always good, right? So if we sub in f of 0, we get f of 0 plus f of 0 equals to f of 0. So we're essentially saying two of one thing, right, is the same as only one of the one thing, right? Which is kind of weird. But this only happens when f of 0 is just equal to 0, which gives us a key piece of information. And another really nice tip when it comes to functional equations is sometimes, but not always, we're going to be able to guess a particular solution of the functional equation. And when we guess this particular solution, it's nice to just keep this solution in the back of our mind because it might help us guide us in trying to solve the functional equation. But even if we just like think about this particular solution, we can't assume that it's our whole solution, right? So we have to remain open to all possibilities. Okay, and knowing this, we can sort of guess that the solution to Cauchy's functional equation is y equals to cx, okay? And after subbing in x equals 0 into our functional equation, we get that f of 0 equals 0. But after that, there are many other things that we can do. One of the things that we can do is f of 1, but this is not particularly useful because when we submit f of 1, we just get that f of 2 is equal to f of 1 plus f of 1. But as I said before, if we sort of are able to guess the solution, we can get that f of 2 is equal to f of 1 plus f of 1, which is equal to 2c. And this is important because we can actually extend this to having y equals to 1 in our functional equation be set to 1. Sorry, yeah. We can set y equal into, we can set y as 1. And when we get that, we can find out that f of x plus y is equal to f of x plus f of 1, which equals to f of x plus c. And why is this particularly useful? Well, it's useful because we've basically found sort of like a recursive formula for our functional equation. So we found that the value at the next point is equal to the value at the current point plus c. And now that we have this recursive solution, we can basically just apply induction. And that's how we're going to get the whole set of positive integers. Yeah, so now that we're done with positive integers, let's go on to finding out how to do negative integers. And since we've already deduced that f of 0 equals 0, we can do this sort of trick where we have f of 0 is equal to f of x plus f of minus x. And from this, we can get that f of minus x is equal to minus f of x. And so not only have we proved this for all positive integers, we have now proved it for all negative integers. Yeah, are there any questions on that? No? Okay. All good. Yeah, so now we're going to try to do it for all rational numbers. Well, like before, we can sort of start with this trick. We can take a number m and we can split it into n parts of that m, right? So we get that f of m over n plus m over n plus all the way to m over n, right? Is equal to f of m on n plus f of m on n, and this would occur n times, just like this, as we've split m into n parts. And from this, can anyone suggest what we might be able to do? Yeah, that's all good. Okay, yeah. So what we can do after this is we can get that f of m is equal to n of f of m on n, right? Because we have this n times. So basically what we've done is we've extracted the n. We've like factorized it out of the this f of m term. And from this, and knowing that our solution to the positive integers is y equals to cx, we can get that f of m on n is equal to what f of m, which we know to be c of m over n. Yeah, so now we've deduced it for all rational numbers. Okay, and so I should have briefly outlined the structure of today's presentation. And basically what it's going to be is I'm just going to teach you a bunch of, I guess, techniques when it comes to functional equation solving. Now let's have a look at this new question. Find all functions f from the domain of rational numbers to the real numbers such that f of x plus y is equal to f of x plus f of y plus 2 of x, 2 times xy for all rational numbers x and y. Okay, does anyone have any idea on how we can solve this? Or any, like, I guess, observations of what this looks like? Yeah, f of x equals to x squared. Okay, that's a really good observation. We'll save that thought for a bit later, yeah? So one of the things that you could think about also is that this is almost Cauchy's functional equation, but instead we have this, I guess, this extra bit, right? We have 2 times xy. And as Jeffrey said to everyone, we can also observe that when we expand x plus y squared, we get x squared plus y squared plus 2xy, right? We get, I guess the trick here is to see that 2xy actually comes from x plus y squared, which I'm guessing that Jeffrey noticed. So as we can see here, if we take x squared to be our function and we apply it to this, we also get the right hand side. Yeah, nice. It came to you in the dream. Okay, but as I said before, we can't always just think about this as our only solution. We have to question that, right? And the trick here comes next. Yeah. So now that we know that f of x equals x squared is a solution, we can try this. We can try sub in f of x equals to gx plus x squared. And I guess, as you can see from the slide title, all we're doing here is we're just guessing something and we're hoping that's going to be correct. But this also reminds me of, I guess, when you're solving like second order differential equations, right? So you always have like a particular solution, which in this case would be x squared, but you also have like your homogeneous solution. It's sort of like that. Okay, yeah, so now that, so we're going to sub in, we're going to try g of x plus x squared, right? And we get this, we get g of x plus y plus x plus y squared is equal to, yeah, this bit, right? Just take a couple of seconds to read this and digest it. Yeah. Okay, so when we I guess when we simplify things, we get that g of x plus y is equal to g of x plus g of y. Okay, so does anyone know what that is? Just write in the chat. Okay, yeah, that's all good. Yeah, so it's the Cauchy thingy. As we mentioned in a couple of slides before, this is Cauchy's famous functional equation, and we know this, right? We've done it before. The solution to g of x is actually equal to cx, right? And so we can finally decipher that our solution is going to be f of x equals to g of x plus x squared, right? But in this case, we found that g of x is equal to cx. And so our final solution is squared plus cx. Awesome. Okay. Did everyone have any questions for that? I'll just take a couple seconds. Okay, all good. Okay, yeah. I'll pass it on to Oda now for substitutions.
All right, great stuff, Felix. Yeah, Cauchy's functional equation shows up a whole bunch, and maybe it's important to note that the special thing about Cauchy in that case is it's from the rationals to the reals. If you wanted to look at Cauchy on the reals to the reals, you would get a whole heap of other solutions that aren't so nice. But it turns out that the ones that aren't CX, they're really, you can prove that they have all these weird properties. And maybe it's worth looking that up after the workshop. But we'll move on to substitutions, which are maybe a more practical topic in terms of solving arbitrary functional equations. So this one here is a little bit of a mess, but we'll see what we can try to do to get our heads around it. So the idea with substitutions is we want to find things that cancel parts of the equation out and make it simpler to look at. So here you can see we have, on the left-hand side, we have f of x plus y. Something nice to have there might be f of 0 instead. We could easily get that if we substituted y is negative f of x. On the right-hand side, you can see that in the first term, we can also get f of 0. If we make a different substitution, y is x squared. And in the second term on the right-hand side, we can also get f of 0. And f of 0 is nice because it's a constant. You could also have f of 1, f of 2, but you tend to end up with f of 0 in competition problems because they're structured nicely. So we'll move on to trying some different substitutions here. All right, let's move on to the next slide. And we'll try negative f of x. Of course, we get f of 0 on the left-hand side. And on the right-hand side, we get something strange, maybe arguably simpler than the first equation. But if we move on to the next slide, you can notice that now we kind of have two different equations that we've made from this first one. And we see that any solution to the first one has to satisfy both of these. And thinking maybe in terms of simultaneous equations from regular algebra, you want to find common components that you can cancel out here. So both of these have this f of x plus x squared term, and both of them have an f of 0 term. And the only difference really is in where those terms are and in that second term on the right-hand side. So if we move on, well, we can combine these two equations into one equation, and we might lose some information there, but it is the case that any solution has to satisfy this relationship that we've derived here. And so if you factor out f of x here, we can see that either, because we have two different factors and they multiply to 0, one of them has to be 0. And in fact, in the question specification up at the top, it told us that either x was going to be 0 or f of x was not going to be 0. Which means that we get a very nice solution here because if x is 0, then either f of x is 0 or f of x minus 0 squared is 0. So we know what f of 0 has to be, and we know what f has to be when x is not 0. So we have a unique solution for f.
All right. Wouldn't we still need to check the solution because we lost information when we went?
Yeah, that's a good point.
Yeah.
But yeah, you could go and sub it back in. That's worth doing in the competition setting. In this case, I don't think we actually lost any information, but it's possible that we would have. Thanks, Ezra.
Cool. All right. Any other questions about that stuff before we move on to injectivity and stuff? Real good. Cool. All right. So, yeah, so we have a couple of definitions we want to go over quickly, just in case you're not familiar with them. So the first one is injectivity. So when we're dealing with functions, injectivity means, you may have also seen it as one-to-one. It means that it doesn't take the same value twice. So when you're dealing with functions, your graph is not going to look like this. In this case, it's called the vertical line test, but you can draw like horizontal line test. You can draw a horizontal line here, and you can see that it takes this value at 2 points. So this function here is not injective, right? On the other hand, monotonic functions, if you know what that is basically just a function that continually goes up, continually goes down, or whatever. They're always going to be injective. So injective functions say that if this value here and this value here on the y-axis are the same, then this value here and this value here are exactly the same. Obviously, in this case, it's not. The next thing we're going to look at is surjectivity. So a function is said to be surjective or onto if it takes all possible values in the codomain. So when you're defining functions, you write them as f maps some set 1 to set 2. And what surjectivity means is that no matter what you look at in this set here, you can always find something that maps to it. So a classic example would be, for example, the function x squared. If you draw a graph of that, it looks kind of like that, albeit less lopsided. And if we wrote this function as a map from the real numbers to the irreal numbers, this would not be surjective because, for example, the value -1, there is no x such that x squared is equal to -1 inside the real numbers, right? So surjectivity is kind of a, I suppose, more formal definition. It doesn't really relate to the graph or anything, but you need to make sure that everything in the codomain is hit, right? And finally, if you kind of join them together, you're going to end up with something called bijective, which is it's both injective or surjective. And surjective, my bad. And the convenient thing about bijective functions is that there always exists some inverse. So when we're talking about bijective functions and we want to prove something is bijective, we're not going to do this, but a possible approach is to just guess what the inverse is and then show it's an inverse. If f inverse exists that satisfies both of these equations, then you know that the function must be bijective. But there are other ways. In particular, you can show that it's both injective and surjective, and then one of these must exist. There's two different ways. The guessing this kind of thing is a little bit harder. I mean, if it's a simpler function, it's not too bad, but when dealing with functional equations, it can be quite difficult to kind of guess what the function is, let alone its inverse. So let's take a look at an example. So we have some function that satisfies this here, and I believe that's meant to be an R there. I think that's an R. But it's a function from reals to reals that satisfies this kind of ugly equation here. Now, whenever you see a functional equation that's ugly like this, your best bet is probably to try and simplify it a little bit. So can anyone tell me what they might want to try substituting? So we're going to substitute something. A real number, what they might substitute to try and simplify this. Any ideas? Nope. So I see xfx inside of it. Yeah, so x equals 0 is a good choice. We want to try and eliminate this, and it'll also leave this kind of like as some kind of constant so that we have a relationship between y and some, I guess not that, but some kind of function value, right? So that's what we're going to do. We're going to try x equals 0 and vary y, and I'm going to try and clear it. There we are. Yep. So we're going to try letting x equals 0 and vary y, and we get this equation here. Now, what's nice about this is that we're trying to prove surjectivity first. So we're approaching this from the perspective of trying to prove surjectivity. Surjectivity says that if we take any value, we can always find something that maps to it. So we have something on this right-hand side that we can control freely. And as long as we can put something in here, doesn't matter what it is, and get what we want on the right-hand side, we're good to go. So what that leads to is our kind of second substitution, I suppose, of letting b equal to, it's like 1 plus the other, yeah. So equal to f of 0 squared plus y. Another way to say that is for any b, we want to let y equal b minus f of 0 squared. Now, f of 0 squared is some kind of constant, so it exists, this function kind of exists, right? So f of 0 exists, and we're just saying, okay, choose y to be b minus f of naught squared, because then the right-hand side simplifies to b. And in fact, if we were to put in whatever this expression is, now it's an ugly expression, but it's something that we could evaluate if we knew what b was and we knew what f was. If we put in this ugly expression, we will get b, which is what we want. So no matter what b is, we can always find something to put in, this little a down here, that gives us b in return, which means our function must be surjective, right? Yeah, cool. So there's an a for every b, such that f of a equals b, so f must be surjective. So we proved one half. The next half is injectivity. And when you're approaching injectivity, what we're looking for is assuming that f of y1 equals f of y2. So the function value at 2 points is the same. And we want to hope to deduce that y1 equals y2, right? So if f of y1 equals f of y2, then we have this here, right? Because they are the exact same expression. So we've looked at the left-hand side of our equation and we've seen some kind of f here, f of y, that we can make equal. And because the left-hand sides are equal, the right-hand sides must be equal, which gives us these two equations here must be equal. Now, what we've done is we've turned a relationship between f of y here into a relationship between y, which is exactly what we're trying to prove up here, yeah? So if we were to rearrange this, we could cancel out the f of x squared because x is any number, right? You can just fix it if you want. X is any number, so those two cancel out and you get y1 equals y2, which means that the function must be injective, and because we proved that it was surjective, we know that it must be bijective, hence the result. Any questions about that before we move on? So a lot of the time when we're dealing with injectivity, bijectivity, and all that kind of stuff, we'll be looking for trying to relate the function value with what you kind of put in. So for injectivity, we're looking to relate this f of y2 and f of y1 with this y1 and y2. So whenever you see a number just on its own outside of a function, it's kind of an indicator that that's what you're going to be looking for to conclude injectivity or surjectivity. Something to do with that could help. How do we get from line 1 to line 2? Hang on, go back. Oh, from here to here. So the functional equation we had was f of x, fx plus fy is equal to f of x squared plus y, right? So that's the functional equation we had, and then we just apply it to both sides, where y gets replaced with y1 or y2, depending on which half of the equation you're doing. Yep, cool. All right, so the next thing is about the associative trick. So when we're dealing with functional equations, you'll end up with situations where you have one function within another function, right? And what we know is that function evaluation is associative. So you can either evaluate f of g first and then sub in h of x, or you can evaluate g of h first and then put that all into f, right? So as an example of a question that might use this, we're going to ask, do there exist functions f and g that satisfy both of these equations here, right? Now, this is kind of a prime setup for the associative trick because we have how you can kind of, in two different ways we can evaluate these functions, and we know what they are, like specifically. Now we're asking if there exist functions, so the answer is either going to be yes or no. If there exist functions, then you can kind of just, I suppose, guess them or deduce properties that they must satisfy, and then from that, find the functions. But if they don't, then we're looking for a contradiction, right? So down the path of contradiction here, we're going to try and find some facts which together give us a contradiction. So in this case, we're going to start off with injectivity. Now, injectivity here is a little bit kind of difficult to see where we might be able to get this. The nice thing about the functional equations we've been given is that if we started off with f of x, this relates double application. So application of another function to this gives us something that relates to x, right? It doesn't give us x, but it gives something that relates to x. So it's kind of like reducing the amount of functions that are kind of there. Now, the problem is to take f of x and turn it into something relating to x. So what we naturally do is we say, okay, if f of a equals f of b, then if we apply g to both sides, we now can use our functional equation, not that one, sorry, this one here. We can use our second functional equation to write them out as the function inputs instead of the actual function values. And because cubing is a bijective function, or it's invertible basically, we can switch it back to a equals b. So we must have injectivity. One thing to note here is if you started off with g of a and g of b, you would end up with a squared equals b squared, which doesn't give you enough information. So in this case, if you were in a test or something, you would probably just try both and see what kind of information you can gather out of these. And then one of them would give you what you want for injectivity, right? So just try things, you'll start to see facts that you might be able to bring together into a proof. So further, we can start to actually apply the associative trick. So the previous part was just showing injectivity by trying to reduce the amount of function applications we had. Now this time we want to use the associative trick. So we do have some relation between f of g, which allows us to conclude that if we apply f, g, f to x, we're going to end up with f of x squared. And if we apply g of f, we end up with x cubed on the inside and f on the outside, right? So we have some relationship between this left-hand side and this right-hand side because they're equal. So we can conclude that f of x squared is equal to f of x cubed. F of x whole squared is equal to f of x cubed. So this is true for every x. And we know that if we substitute in a few values, we have that f of minus 1 is equal to f of minus 1 squared, f of 0 is equal to f of 0 squared, and f of 1 is equal to f of 1 squared. Can anyone tell me what this might mean about our function? So what possible values do we think that these three things can be? Any ideas? No? So each of these is effectively y equals y squared. Exactly. So they can either be 0 or 1. If you were to actually solve this, you'd have like y squared minus y equals 0. So y minus 1 equals 0, so on and so forth. Now, the thing is, because we have three things here, and we only have two possible values. This can be 0 or 1, this can be 0 or 1, and this can be 0 or 1. At least two of these must be equal to either 1, or two of them must be equal to 0, just using pigeonhole principle, right? Now, can anyone tell me what I might be able to use here to deduce some kind of conclusion? So we know at least two of these are the same. Yes. In the previous slide, we just showed that the function was injective. And injectivity means that you can't have the same function value twice. However, we've just, by pigeonhole principle, concluded that at least two of these are the same value. So we've contradicted our injectivity assumption, which means that basically starting from the assumptions we were given in the question, g of f is equal to x squared and f of g is equal to x cubed, assuming that they existed and going from there, we ended up with a contradiction, which means, in fact, no such function can exist. So we've just proved no such function can exist. If you were to try and prove that one existed, it would probably be a little bit more difficult because you'd be looking for some actual function. So to answer that question, you would have to show that one exists, by which you would just show that a function satisfies these things. Eventually, you would end up probably coming to this contradiction because the way we did the contradiction was to just kind of assume that it worked and then see what things it needed to satisfy, to which we got a contradiction. If you were looking for an actual solution, you would probably also start with just seeing what you can kind of conclude from there. And if you can conclude some things that you can use to create a function, that's great. If you conclude things that are contradictory, then that's also great because you've answered the question. So both kind of ways these problems can come up, either existence or showing that one doesn't exist, should end up giving you the same kind of path to a solution, I suppose. Just chucking things together until either you get a contradiction or you find a function. Yeah? Any questions about any of this, by the way, before we move on? No? Okay, cool. That's all from me then.
Okay, let's get my camera. I got my camera on as well. Now exploiting symmetry. The main idea behind exploiting symmetry, I can show an example. Wait, my mouse. If we have, let's say we have A equals B, and now if A is a symmetric expression using some variables, for example, x squared plus y squared is symmetric in x and y. But let's say B is asymmetric, so B has some sort of asymmetry. So an example of asymmetric expression, you could have x plus 2y. So if you swap x and y here, you get two different expressions. But now, what would happen if I swapped x and y? If we swap x and y, so it's not the greatest example because this is mainly applied for functions. So this is mainly for functional equations, but here I could put some f's around it. So if I have f of x squared plus f of y squared, if I have f of x squared plus f of y squared, you can see if you swap x and y, you still get the same expression. And let's just change this to f of x plus f of 2y. Now over here, if I swap x and y, we get f of y plus f of 2x, and that is a different expression because now the 2 is in front of the x, but it's not in front of the y when you swap x and y around. So in a functional equation, if you swap x and y, you can see the a still becomes the same, but now you have a different c on the right-hand side. So now what you can now do is, using these two equations, since b equals a and c equals a, you can now write b equals c. So in this example, b equals c means f of x plus f of 2y is the same as f of y plus f of 2x. To get some new information just from swapping x and y, and this equation, in fact, it disappears after you use this exploiting symmetry argument. Usually this technique works when you have something you can make symmetric on one side, but it is asymmetric on the right-hand side. Let's have a look at this example here. Find all functions from integers to integers, and f of n plus mfn is equal to m plus mn plus fn. Okay. So right now we don't really have any symmetry just in this original equation. So when you swap m and n, both sides they change. So currently both sides are asymmetric. But the trick here is we can make the left-hand side of the equation symmetric. And this is an interesting substitution. We are making m equal to f of some other integer p for some integer p. And the reason why we're doing this is, see the m's here, and if you just change the m's with f of p, you now see this f of p plus f of n plus f of p f of n expression is now symmetric, because if you swap p and n, you still get the same thing. However, the right-hand side, if you put f of p here, you can still see f of p plus f of pn plus f of n. This is still asymmetric. And the reason is the f of p times n gets converted into f of n times p, and so you get a different expression involving the functions and the variables. Okay, so go next one. Yeah, so what we notice, the left-hand side is symmetric, so we can swap p and n and still get the same expression. And the right-hand side, Oh yes, now we can use the same trick from earlier. We use this A equals B and A equals C idea. So by swapping P and N, we can have the left-hand side stays the same, but the right-hand side okay. Some technical difficulties.
Sorry, just give me a second.
Do you want me to share mine, Felix?
Yeah, that'd be better, I think. Thanks.
Cool. All right.
Okay, so we have to oh yeah, I think it's a slide before. Okay. So what we've observed from before, if we replace the P with the N, we have F of N plus F of NP plus F of P. And this is using the same idea of the A equals B and A equals C and implies B equals C. So the original equation, the right-hand side is the same thing as here, the F of P plus F of Pn plus F of N. Now after swapping P and N, the expression is still true because remember the function equation holds for all integers M and N. So even by doing some swaps around, you'll still get the exact, the left-hand side will still be equal to the right-hand side. The left-hand side doesn't change, but the right-hand side now becomes this new thing over here. We have a new right-hand side with the same left-hand side. And this means we can equate the two different right-hand sides to get this equation over here. Okay, so now we also get some cancellation. So I guess in the previous slide, the F of P's and the F of N cancels out, and all of it simplifies down to F of Pn equals F of NP in the next slide. Okay. I have F of Pn equals F of NP for all integers P and N. Now equation's looking a lot simpler. So now we still have two variables P and N, so we can do a lot of different substitutions, and much simpler scenario than the very beginning. Okay, so we can do quite a simple substitution here by just putting P equals 1, and what we have is F of N. So P equals 1 here, so we just have F of N on the right on over here, and now we have F of P, so P is 1, so we have F of 1N, and we have Cn. So this gives us F is a linear function, so constant times N, and the constant is some integer C. Okay, now, so usually when you do the functional equations, when you make these substitutions, you might lose some information. For example, when you did the exploit symmetry argument, the left-hand side was completely gone because we only used two different right-hand sides in our argument to prove it's linear. So maybe that the original equation is not satisfied, so we still have to check the original functional equation. So what it turns out is, if you substitute in, it turns out the only possible value is c equals 1. And even though we get linear functions here, most of the linears don't work when you put into the original equation. And that's because you can find some substitution of values that can disprove every case of c not being 1. And it turns out the function equation is only satisfied for all values of n when f of n is equal to n. So we only get the identity function. Okay, so that is example of the exploiting symmetry. So yeah, the main idea is when you have something symmetric on one side and asymmetric on the other side, you can equate two different asymmetric expressions and to hopefully simplify the situation. Okay, so now moving on to involutions. So involution is a function which is its own inverse. So we have f of x equals x. So if you remember inverses, we usually you have f inverse x equals x for all x. So when the inverse exists, in this case, inverse of the function is itself. So same as saying f inverse of x is equal to x. This is f inverse of x is equal to f of x. Now this happens for all x, and a nice property about involutions is it's both one-to-one and onto, so it's both injective and surjective, so it's bijective. And reason for this is, since we have f of x equals x, we can get all the possible x's on the right hand side. And also it's injective because if you had two function values that were the same, so f of a equals f of b, if you put it in here, if you put it into this equation, you will automatically, it turns out you can automatically get a equals b from here. That's a nice property about involutions. Okay, so now I can move on to the example question, which is find all functions g from the reals, apart from this 2/3 number. So all the reals except for this number, and codomain is the reals such that x minus g of x is equal to half g of 2x/3x minus 2 for all reals apart from the 2/3. So this 2/3 is just to ensure the denominator is not equal to 0. So just ensure the function is defined for all x. This is a functional equation in one variable, which is quite interesting because most of the other functions have two or more variables. Usually the one variable functions can be hard because there's less degrees of freedom. You can only choose one, you only have one choice to make, which is x. So you can't choose x, you can't choose both x and y. So usually these one variable function equations can be tricky. So have a look at how involutions play into this functional equation. You're comparing, so you have two different values of, you're evaluating here two different values. So we have x and we also have 2x/3x minus 2. And the question is, so x must be related in some way to this 2x/3x minus 2 function. But so can we do something with 2x/3x minus 2? is the question. So this is, so we have the variable x, and using x we get this new expression here. But the question is, what if we try, instead of having x here, what if we try inputting 2x over 3x minus 2 and replace it with x? And what you can see what happens if we try that. So on the next slide, we'll have a look at what happens. 2x. So now what's happening is we're replacing x with 2x over 3x minus 2. And now the x minus gx now becomes 2x over 3x minus 2 minus the g of 2x over 3x minus 2. And so everywhere we see x, it gets replaced by 2x over 3x minus 2. Okay. Now doing some algebra here, and so this expression inside the right hand side, it simplifies quite nicely just by, we multiply numerator and denominator by 3x minus 2, we get this over here, and in fact it simplifies all the way down just to get x. So what it turns out here is this function 2x over 3x minus 2 is an involution, because if you apply it twice, you'll get back x. So in this case, the actual function g is not the one that's necessarily an involution, but here it's actually the expression inside g is the one that's the involution. That's 2x over 3x minus 2. Okay, so now we have two different equations. Okay, I think this should say, I think this should have g in it. Wait, I think the second equation should be this one. So that's equal to g of x. So two equations. So the first equation was just the original functional equation. Now we derive the second equation, which is g 2x over 3x minus 2 of minus this is equal to g of x. Now we have two equations involving g of x and g of 2x over 3x minus 2. Yes. Does anyone want to have any ideas of how we can just find what g of x is? This is a common technique from high school maths, maybe between year 7 and 9. So I guess it might be a bit disguised. Can anyone see how you can just get what g of x is? So I got in the chat, we got Ezra saying simultaneously solve for g of x, and that is the correct answer. Because the g of 2x over 3x minus 2 may not be too helpful for us, but just get, we can somehow eliminate the g of 2x over 3x minus 2 and just get g of x. That will help us have an equation with just g of x in it. Okay, so you go to the next slide, and we'll get, so yeah, two simultaneous equations, and if you solve the simultaneous equations, you end up getting g of x is equal to 4x times x minus 1 over 3x minus 2. And just as for all the previous examples, you should check this is in fact indeed a solution to the original function due to the reason of the losing information when you make the substitutions. So that concludes this example for involutions. Okay, so I guess that's it for involutions.
Yes, Siri, do you think, what was it that you think motivated the idea that 2x on 3x minus 2 might be an involution? Like, is there something that you're seeing in that expression that's making you think involution?
So usually, yeah, I think it's hard to see from sight it's an involution. However, for these one variable, when there is one variable function equations, usually there's not much you can do. So usually x is related, so as mentioned earlier, x is related to 2x over 3x minus 2. You can try to get a chain of relations. So if you keep on trying to substitute the new expression back into the original expression, you can get a lot of equations. And I guess if you're lucky, it can be eventually periodic. So you eventually get back to x. Then you can simultaneously solve for lots of equations, lots of variables, and isolate the x. And here we are lucky because just substitute 2x over 3x minus 2. It's an involution itself. But in other cases, you may have to apply the function to itself a lot of times to get back x. So, for example, if you apply f 3 times to x, you might get x, or it might take 4 times or 5 times. So this is a more special example.
Yeah, so I guess Ezra's pointing out that it's a Mobius transform, and you can look at the pole and the asymptote are the same. So if anybody's taken or is taking complex analysis, maybe you'll recognize that kind of expression there. But we'll move on. So we're at the end of the presentation now. So we'll move on to the working on the problem sets. And if you want to join the Discord server, I'll post that link again. And also fill out the attendance form. Then you can join one of the channels, work on the problem set, and I'll post the link to the problem set as well. Great. Thanks for coming, everyone.